Section 6.2, Part 2, Solving Systems Using Substitution. I can solve systems of equations using substitution. Again, the big idea is here, systems of equations can be solved in more than one way. And when a system has at least one equation that can be solved quickly for a variable, the system can be solved efficiently using substitution. So in example 3 here, it says, a snack bar sells 2 sizes of snack packs. A large snack pack is $5 and a small snack pack is $3. In one day, the snack bar sold a total of 60 snack packs for $220. How many snack packs did the snack bar sell? Okay, so we're dealing with two totals here. We're dealing with a total of 60 snack packs and a total of $220. So we're going to have two different equations here. One is going to deal with just how many snack packs. We have small and we have large. So I'm going to use M for small because S's are hard and L for large. So the total number of large and small snack packs was 60. So this one deals with quantity. The second one, we're dealing with money. We're talking about cost. Okay? The cost for a large snack pack was $5. So it's 5 times L. Price times quantity give us cost. Plus, since we're talking about total, it is $3 for a small snack pack. And the total cost was $220. So this is our system. When we look here, we have L and M that are both fairly easy to solve for. It doesn't matter which one you pick. It does not matter. I'm going to subtract M, and now I'm going to have L equals 60 minus M. Again, you could have solved for M as well. It does not matter. Once I know, though, what L is, I can substitute that in for L in my second equation. The equation itself doesn't change except for L. L is going to be 60 minus M. And the rest of it we bring down exactly as we wrote it. Now to solve, we distribute. Combine like terms here. In order to get our variable by itself, I'm going to subtract 300 and divide by -2. Remember that the sign goes with your number right there. So we have 40 small snack packs. To figure out how many large there are, okay, we plug it in. We know that smalls are 40, so the large was 20 large. So how many snack packs did the snack bar sell? They sold 20 large and 40 small. That's the only combination that would give them a total of 60 things sold and $220 in cash. Go ahead and pause and give this a try if you'd like. Now, you pay $22 to rent 6 video games. The store charges $4 for new games and $2 for older games. How many new games did you rent? So we pay $22, that's our total amount of money, so our total cost, for 6 games. That's our total quantity. Our cost is $22, and that's for some new games and some older games. I'm going to use D for older because O's are hard. So the new games in our cost, $4 each, so price times quantity. And the older games are $2 each, so price times quantity. And that gives us our cost equation. Our quantity equation says that we have 6 total video games. Some of them are new, some of them are old. We want to know how many new games did we rent. Again, just like with the last one, it doesn't matter which variable we solve here, n or d, because both are going to give us fairly easy equations to work with. Now that I know what n is, I can substitute that in for n in the other equation. The equation stays exactly as it's written, except for when we substitute in the n value. Now, to solve, all I have is one equation with one variable, which is perfect. 24 minus, 4d plus 2d. Combine like terms. Get our variable by itself by subtracting and then dividing. So d is going to be 1, which means our older games was 1. To find out how many newer games, we substitute in and get 5 new games. And that's what the question is asking for, how many new games. Just like we learned in section 6.1, when we solve systems of equations, sometimes it's possible to get infinitely many solutions or no solution. And that can happen algebraically as well. How many solutions does each system have? In A, if we look, x is already solved for. We know that x equals negative 2y plus 4. So we can substitute that in for x. Our equation stays the same, except for where we substitute in that x value. And again, we bring down the rest of it exactly as written. Distribute. Combine like terms, and negative 7y plus 7y gives me 0 y's. So all I have left is 14 equals 14. Since that's true, it's infinitely many solutions. These two equations, if we solve them both for the same variable, would look exactly the same. Okay, now in B, we know that y is 3x minus 11. So we can substitute that into our second equation. And the rest of the equation stays exactly as it's written. When we combine our like terms here, 3x minus 3x gives me 0x. Negative 11 equals negative 13, which is not true. So this is no solution. Something to be careful here, guys. Anytime we substitute in, we have to substitute into the opposite equation. If you substitute into the same equation, like if I solve this one for y and then substitute it back in for y, we're always going to get, or should get, 0 equals 0. And that's not what we're looking for. We have to substitute it into the other equation. So since I took y from the top and plugged it into the bottom equation, and my variables canceled out, we know it's either going to be infinitely many solutions or no solutions. Here, since it was not a true statement, it was no solution. Feel free to pause and give this one a try if you'd like. If we look here, it doesn't look like any of these systems are going to be super great to solve for a variable. So I'm just going to pick one. And I'm going to pick this 6y. 2 reasons. I don't want to deal with this equation because it has a decimal in it. So when I solve there, it gets extra tricky. And when I substitute into a y in the second equation, I distribute a 3 instead of a decimal. So you could have picked any of these to solve for, but that's the one I'm going to solve for, which means I'm going to subtract 5x first. And then divide by 6, and when we do that, we do it to every piece. And we can reduce along the way. Now that I know what y is, I can plug that in for y, and again, it has to be in the opposite equation. So 2.5x plus 3, we substitute in our y value. That's the only part of our equation that changes. And distribute. When we distribute here, we get, this is going to be 5 over 2x, which is also 2.5x. And I switched it to a decimal there because we have decimals in the rest of our equation. It doesn't matter which one you put it as, but it's going to be easier to combine like terms since I already have decimals if I write it as a decimal. Now combine your like terms, and I get 0 x's. So all I have left over here is a 4, and that equals 4. That is true. So since it's true, it's going to be infinitely many solutions. A quick recap here for section 6.2. Systems of equations can be solved in more than one way. When a system has at least one variable that can be solved quickly for a variable, the system can be solved efficiently using substitution. And as long as we substitute from one equation into the other, if our variables cancel out and we don't have any left, it's going to be either infinitely many solutions or no solutions. And that's all for the second half of section 6.2.